Today, I'm going to be taking a closer look at these LM75 based temperature sensor modules. I got a couple of these in a recent mailbag, and I figured I'd just spend a little bit of time playing with them and seeing what they can do. The first thing that I've discovered is that they are just a temperature sensor. A lot of the other temperature sensors can also do humidity or barometric pressure, stuff like that. This one is strictly for temperature. It connects to microcontrollers using SDA and SCL, otherwise known as I2C. And being an I2C device, you can choose its address from a few different options. There's a base address, and then if you jumper one or more of these pads, it will increment the address, so you can have multiples of these on a single data pair going back to your microcontroller. In addition to the connections for power, ground, and SDA and SCL for the control, there's also this OS, which is, I believe it's called over temperature or something like that. Basically, you can set a temperature threshold in this thing, and it will trigger that pin when you exceed that temperature threshold, which could be very handy in an awful lot of circuits. Let's take a quick peek at the data sheet, and then we'll grab a microcontroller and throw some code at it, I guess. So among the things that the datasheet talks about is a wide power supply voltage from between 2.8 and 5.5 volts, so it can be used with Arduinos and any of that family of microcontrollers at 5 volt logic, or with the ESP microcontrollers or the Pi Picos that run on 3.3 volt logic. So that is nice. It runs on I2C bus with up to 8 addresses. We saw that with the address pins on the back. It can read temperatures from minus 55 Celsius to plus 125 Celsius. So that should be adequate for the weather we get around here. And it's running an 11-bit ADC, so temperature resolution of 0.125 degrees Celsius, which is pretty good. I'm not going to read every single page of this 24-page datasheet, but there is the block diagram of what's going on inside. There is the 3 address lines, the I2C lines to ground, and that OS, which is over temperature shutdown, looks like it's an open drain of a MOSFET, so it pulls to ground. It'll sink current. I wonder how much current it will sink. I wonder if I can run an LED off that or something. Yeah, here it's talking about that OS comparator mode. The OS output acts like a thermostat, so it becomes active when the temperature exceeds a set point, and then it's reset when it drops below the hysteresis version. So you can set both a trigger and a hysteresis so that it's not, it's got a bit of a band gap in it, which is nice. And then lots of information about how to decode the data coming from it. I'm hoping that I won't have to deal with this. I'm hoping that I can just find a library that will do all the hard calculations for me, so I don't have to think about it, because as I've said many times in the past, I am really bad at code. It just doesn't mesh well with my brain. So if I can rely on libraries from somebody smarter than me, I would do that every day of the week. Oh yeah, and there's something else that it talks about. It's got a shutdown mode. Basically, this is a power saving mode, so you can have your microcontroller put it into shutdown mode, save fairly significant current, only drawing 3.5 microamps when it's shut down. So if you're running, like I said, a remote temperature sensor on batteries or something, you can tell the thing to shut down for 90% of the time and just wake up, take a measurement, and shut back down again. Okay, here is the physical ratings. Power supply voltage up to 6 volts maximum, both power supply and for interfacing. So again, between 3 and 5 volts should be no problem at all. The output sync current, 10 milliamps. I guess I could run an LED off that, but it's probably intended simply to run to another microcontroller pin. But we'll play with that a little bit, I suppose. Actually, it looks like I don't need to add an LED to that OS pin, because it's already got one sitting right there with its own resistor, presumably current limiting it. So that makes it even easier to tinker with this thing. So I'll just connect it up to this Arduino Nano here. just because it's in a convenient form factor. It doesn't take up too much room on my desk. I could have used any Arduino, but that one just happened to be handy. So now then, I guess we're going to want some code for that and a library, presumably. So back to the computer. Going to the official Arduino documentation, I've found that there is not just one LM75 library. There are actually 3 of them. Interesting. And presumably each one of them has its own set of examples. I guess I'm going to spend a little bit of time downloading those and installing them. And, well, let's just take a peek at some of these examples. I don't think I'm going to go through every one of them, but, well, let's just play, I guess. So after installing all 3 of those libraries, here's what we got. This one looks like it's got 5 examples. That one's got 3. That one's got 2. So let's start with the basic usage one out of this one. Oh, I recognize that name. I think I'm subscribed to his YouTube channel. Yes, I am. Cool. I knew I recognized that name. Anyway, that's a distraction. Let's see what this thing does. Include the library. Yeah, that's all there is to it. What I'm not seeing is this thing calling out the I2C address. So I'm going to assume that it is just talking to the base address, and the one that I've got on the breadboard right now doesn't have any strapping on it, so I'm going to assume further that it's running that base address. Anyway, it is going to use a get temperature command and then display that. Oh, okay. So the library handles even the Fahrenheit and Celsius translation, but it defaults to Celsius because, of course, it does. That's what it's supposed to do. And then it'll print out the hysteresis temperature and the OS trip temperature. Oh, okay. And then it also demonstrates that shutdown and wake up again. And okay, well, let's dump that onto our Arduino and give her. All right, so it does exactly what we thought it would do. It shows the temperature in Celsius and in Fahrenheit. The hysteresis is currently programmed for 75 and the trip at 80, so the OS will go active at 80 and will release at 75. And then it's doing its little shutdown and waiting and repeating the whole thing again. So we're 22.37 currently on my workbench. Or at least that's what it's telling me. Let's see what the infrared has to say. 3.9 or 24... 23 point something or thereabouts anyway. So that's a degree or so off, which I guess isn't too bad in the grand scheme of things. Let's test out the temperature thresholds. So that OS trip should happen at 80. And when it does trip, that little LED there should go on. I'll just apply a little bit of heat gun to it. I've only got it set to 100 Celsius, so I'm not going to kill anything here. We're seeing that the temperature is rising. So there. Oh yeah, look at that. We have a light. Cool. So hopefully when that drops below its 75.0, it should turn the light off. And there it is. Now I wonder what will happen if we are not talking to it. Can I program that thing? Well, we know it's set for 75 and 80 right now. So let's just disconnect the SCL and SDA lines and reheat this guy and see if it will operate completely independently, which would be pretty cool if you could program it once and then have it just go off. But I don't know if that's possible. Okay, no, that's over 100 and the LED hasn't come on, so it appears that it does need the microcontroller intervention for that to happen. Yeah, all right. Well, that's too bad. I mean, if you're building a microcontroller controlled thermostat, you're going to leave it connected and communicating anyway. But I thought that would have been a cool application if you could have just used it standalone. Regardless, let's see what these other libraries have to say for themselves, shall we? How about this one, LM75 Get Temp? Oh, this is interesting. This library comes with a sketch that doesn't use the library. Yeah, okay. So I guess we can see what's going on. So it uses wire.h, which it has to for I2C. It does a little bit of definition here. It defines the base address, which is 48 hex, which I guess is the base address. You could change that if you want to, if you got it strapped differently. Create some floats and stuff. Sure. And then it is sending a request, and it is reading stuff, and it is doing some math, and it is printing it. Okay. Let's see what happens. What happens is exactly what we thought might happen. It is giving the temperature in degrees Celsius and degrees Fahrenheit. This is super basic. It's just getting the temperature. And again, if we throw the heat gun at it, we should see the temperature change pretty quickly here. We are not seeing the temperature change. We're not seeing the temperature change. Yes, the temperature definitely should be changing. I'm not a fan of that one. Let's try something else that actually uses its library. Maybe it's not working properly. I don't know. Where is it? It's that one. How about functions? There. This one is actually using the library. So it is max, min, and temperature. What is it doing down here? It's checking if it's connected. It's setting the thresholds to 25 and 30 for the OS. Okay. And then it's getting them and printing them. Sure. Let's, oh, and it is doing shutdowns as well. Okay. So what are we seeing here? LM75 is connected. Yeah. Min is 25, max is 30. It's currently 34. So that should mean that the OC should be lit, right? Not the OC, the OS. But it's not for some reason. So let's change that to 35 and 40, which is warmer the thing is, and re-upload it. And we'll just see what that does. So it's connected. There's our 35 and 40, and it's 31 right now. Oh, and the light is on. Why is the light on? And what happens if we warm it up? The light goes out. Huh. So that must have inverted the logic or something. That's unexpected. I must have missed that in my hasty reading of the script. But then again, as I said earlier, I'm not really that great at reading code anyway. Let's try the other library. This one had multiple different things. Hey, there's a multi-sensors one. Okay. Let's see what that one looks like. Now, this one is using address 48, which is default, and address 49. And it is reading, it's just reading both temperatures. Okay. Well, let's quickly solder up the other one and add it onto the breadboard then. Nothing to this. As I usually do, I'll just put it into a cheap breadboard, which is what I'm using here, and that'll hold things all nice in alignment. Use a bit of blue tack to keep it nice and parallel. And there is the pins. Now then, the addressing. And that should be as simple as putting a solder blob between VCC and the first address pad here. Ooh, that solder resist is working quite well. There, massive solder blob and not shorting to the ground. So I think that one should be recognized as 49. And because it's I2C, we should just be able to parallel up all of the pins, and it should just go. After, of course, we throw this sketch at it. So there's the two sensors. One of them says 25.5, one of them says 26. And if I throw some heat at sensor 2, but not sensor 1, yeah, we're seeing them all changing up. That is excellent. It's also completely unsurprising because that's exactly what it's supposed to be doing, but that is very straightforward. The commands are easy to understand in all three libraries, really. Let's try this in one other situation. With a Raspberry Pi Pico, aka an RP2040 chip, but more importantly, that chip runs on 3.3 volts logic, and it'll be running MicroPython. If I can get MicroPython to talk to this thing, then you should be able to use it on ESPs and a lot of other microcontrollers as well. And actually, since you can use Arduino to program the ESP32 and ESP8266 families of chips, you should be able to use any of those libraries, I would expect, in that mode. But if you got MicroPython, you should be able to do it the way I'm about to do it here, assuming that works too. So let me just get this all hooked up and find some code for that, or some examples for that. A bit of searching around has come up with this, and I will put a link to that down below. It shows using GPIO 0 and 1 for SCL and SDA. And here is the code. And I'm even less versed in Python code than I am in Arduino code, but this is relatively readable, so we'll just quickly go through it. We've got the imports up here, as usual in Python. The base address is 48 or 048x, and we can change that to 49 as well because we've got the other module sitting here. SCL and SDA defined, I2C stuff, yeah. And then the loop, converting the binary into actual temperature using magic math. And there's that precision again, the 0.125 degree precision that we saw in the data sheet. Okay, so let me just dump that into Thonny and onto the Pi Pico, and we'll go play with it. Well, here it is. Looks like I had a blink sketch on this Pico already, but there is my demo. Just copy and pasted it across, and yeah, it all seems to be there. So when we run that, we get 25 degrees as expected. Now, one thing I noticed in this script, it doesn't do anything with the with that threshold and that OC. I'm assuming a skilled programmer could probably work it out from the data sheet, because all that information is in there telling you what registers and pointers and stuff to do. But again, that is above my pay grade. But as just a basic thermometer, it is working quite well. And we're seeing it coming back down to temperature as you'd expect. Cool. I suppose if we wanted to, we could change this to 49 and then run it again. And that should be the other one, which is this one over here. And yep, we're seeing that happen. Okay. I mean, that is very, very basic, but that is, again, all I needed to know about these things to be able to make use of them for their basic functions. I am a little disappointed that they wouldn't work in that threshold and alarm mode or thermostat mode without a microcontroller connected to it, because I kind of thought that would be a neat way of using them. But regardless, if you're making a microcontroller run thermometer or thermostat or anything like that, then you're going to be there anyway. And that could just be used to either trigger some external thing, like a relay through an optocoupler or something, or you could send a signal back to your microcontroller that it could just monitor now and again for that threshold to be hit. Although, why you wouldn't just do that in software by reading the temperature anyways, I'm not quite sure. It seems like a more useful function that it otherwise looks like in the real world to me, but your mileage may vary. Have you experimented with these chips? Have you used them in any projects of your own? Let me know down in the comments. Anyway, thanks for watching. That was, like I said, just a quick peek at these chips and seeing if I could get them running in a couple of different ways with a couple of fairly standard, fairly basic microcontrollers. And yeah, there's well, especially for the Arduino, there's plenty of code out there, and I didn't even look at all of it. I just looked at the 3 that are linked from the Arduino webpage, and they all worked as expected, and so did that one for the Pi Pico. Anyway, yeah, thanks for watching. I do appreciate it. I will talk to you later. And for the people wondering, the beer has been Stout from Black Wheat Brewing in Brandon, Manitoba. It is, as you would expect, a nice, dark, tasty stout